Great. Okay. So, thank you for the kind introduction and nice good morning from Vienna, Austria, where I'm located. So, I have the pleasure of being the coordinator for the HIGHSPIN project, which I will try to present to you in the next few minutes. I will present. Um, yeah, jumping right in. So, the HIGHSPIN project responded, as I think did most of our projects here, to the D20102 call from 2022. Addressing high performance generation 3B lithium ion batteries. And here there were the possibilities to focus on high capacity approaches or high voltage. In our project, we chose the high voltage track. I'll explain that more in a minute. Um, our consortium consists of 13 partners from 8 European countries. So we work more or less in the full value chain from active materials supplier, so on the industrial scale, through to end users. So we have active material suppliers from industry. We have larger production facilities, and we also have end users providing use cases for the applications. Um, so what are the objectives of the project in detail? We're focusing on the chemistry level on pairing an LNMO cathode with a silicon graphite anode and a high voltage electrolyte. Um, we're also working quite a lot on the actual electrode manufacturing processes. So here we employed two techniques that we refer to as bilayer coating and laser structuring, which I will present a little bit more further on. There's also, of course, work on the active materials development themselves, so on the morphology, on the electrolyte development. Um, then on the cell level, we want to validate the cells in both automotive and aeronautic application profiles. In fact, in HIGHSPIN, we focus particularly on aeronautic because we think that this is the next frontier of electrification. It's a difficult to electrify application. So we want to start making inroads there. We focus also on demonstrating the cells in an aeronautic module. So the target here is to design a module that is very light relative to the cells inside, so that the module will only make up 10% of the mass of the full module with the cells inside at the end. And finally, of course, new chemistries also need to fit into a circular economy. That's why on the recycling side, we're pursuing two recycling routes. So one more traditional hydrometallurgical recycling route and one direct recycling route. And so if you consider all those things, there are a few different areas that we're working on in the project. So chemistry development, as I mentioned, advanced manufacturing consisting of 3D electrode engineering. We also work with aqueous processing of the cathode for better environmental impact. There's the aeronautic module design for the aeronautic use case, and all the work on circular economy. So life cycle assessments, not only ex post at the end of the project, but also during the project. We use this particularly to guide a lot of the module design in the aeronautic space. So due to the brevity of time, I'll focus on two areas and try to provide a bit of an insight. Knowing myself, I tend to talk too long, so that's why I've limited myself in the number of slides. There will be more to say, but perhaps on another occasion. Yes, but let's go right into it. So first on the chemistry development. So in HIGHSPIN, we take an approach that we call iterations. So we aim to develop two new material iterations in the project, and so I should explain briefly what that means. So for us, an iteration is a combination of cathode, anode, and electrolyte. So that's not only the active materials, but the active materials plus the additives plus the processing for the electrode and the electrolyte. So the complete, let's say, processing recipe. This is developed on lab scale, and the most promising candidates then go into upscaling on research pilot lines and on medium-sized production facilities from our industrial partner. So just to give you an example, we have let's say a benchmark from predecessor project that was developed, but in this project we do what we call iteration one and iteration two. So on the cathode side, on the lithium nickel manganese oxide, we've looked at different particle morphologies, so single crystalline and polycrystalline. Um, and on the anode side, we've been looking mainly at integrating higher amounts of silicon into the silicon graphite mix. And by the way, in some of the slides here, you can see that the references to the deliverables where you can find more information because these are public documents, so you can look more into that if you're interested. Just to give an example from the cathode side, so our industrial partner provided various candidates that were characterized. There were different morphologies and particle size distributions, so you can see an example on the right here. So you have either more spherical morphologies or polycrystalline ones. These were all, let's say, tested and built into small cells on lab scale. And what we found, for example, in this particular case was that it was beneficial for our iteration one to mix two LNMO candidates into what we then called LNMO3. So taking both the spherical particle morphology and the polycrystalline one, because if you look on the graph here, for example, the LNMO3 had overall fairly good performance characteristics compared to the other two. And also from a processing point of view, this allowed higher densification of the electrode, so a higher areal loading. Then going on to the 3D electrode architecture side, I think this is a quite interesting aspect of the project. So this is comprised of two components. There's multi-layer coating and high-speed laser structuring. The objective here is to square the circle, if you will, between a few different things that are often trade-offs. So we want to achieve high areal loading on the electrodes to obtain high energy density. But of course, that often comes at the trade-off of reduced rate capability. And so we want to try to balance these two things. Laser structuring also holds the promise of potentially improving electrode wetting and maybe also mitigating cell swelling, particularly on the anode side with increasing silicon contents. So what can that look like in practice, or rather, what is electrode structuring really? It means the targeted removal of electrode material using laser ablation with pulsed lasers. So there are different parameters that we can work with here. So some of them are given here. So for example, we can look to vary the pulse duration of the laser, the number of repetitions or passes over the electrode to ablate the material, the power of the laser, and also the pitch distance between the grooves and etchings that are made in the laser with the laser. So we can consider different patterns that can be etched or ablated on the electrode. So you can see, for example, line patterns, grid patterns, or hole patterns. And then, of course, these different patterns, these different electrodes are assembled into cells and tested for electrochemical performance and potential for upscaling. And one thing that, of course, has to be considered is that because we're removing material, we have a mass loss here. So that means we're removing from the energy density of the electrode. So that needs to be kept in consideration. So just to take one example here of the different kinds of patterns that we could envisage in some of the performance or some of the early performance that we've seen on the cathode side. So if we consider, for example, a pattern with a pitch distance of 200 micrometers, you can see that at higher C rates, this particular electrode tended to outperform. So if you look at the red dots, at increasing C rates, it had a better discharge capacity than unstructured electrodes or those with a higher pitch distance, so fewer grooves. So that's one aspect of the 3D electrode engineering, and the other one, as mentioned, is the multi-layer coating. So multi-layer coating means the application of one coating on top of another coating to increase the aerial loading. So we can do this in two ways, depending on the equipment that's available. So on one hand, we can either coat a single layer and then coat another layer on top of that. So if you look at the left picture, for instance, you just repeat the process. Or we can do a simultaneous dual layer coating using a slot die head. And of course, there have been simulations and sort of process parameters that have gone into to investigate, well, what are the optimal settings for this kind of coating. One of the there are some challenges to overcome with this. One of them is the use of binders and the selection of binders to enable the right consistency and to enable good quality homogeneous coating. And another big aspect here to consider are drying parameters, for example, in the manufacturing process. So these are all things that need to be tried empirically. They can only be simulated to a limited extent. Then on the right, you can see an example of a result of the multi-layer coating. In fact, the thing is that you can actually not really see the transition between the two layers. So this is an electrode coated on both sides with dual layer. And so we're able to achieve slightly higher loadings than what is normally typically achieved with a single pass coating. And that already brings me to dissemination parts. So in HIGHSPIN, when we designed the project a few years ago, meanwhile, one of our one of our foci was to make a lot of the information publicly accessible. So we looked to make a very large proportion of our deliverables public. So 22 out of the 29 total deliverables are public. Right now, at current state of progress, we have about 12 public deliverables that are online, and of course, more will follow as the project progresses. We have 7 publications already published, of which at the moment only 4 are visible in Cordis, but we will update this presently and also on our website. So again, looking to disseminate the findings and the research in this project as widely as possible. And so if you would like more information, you can find us on LinkedIn or follow us on LinkedIn. You can visit the project website. And of course, the official public results are also on the Cordis webpage. Or if there's anything that you can't find there or would like to get in touch with any of the project partners, then of course feel free to email me directly. So I hope, yes, I managed to stay on the time. So I hope that's provided you a little bit of an overview, and it's been interesting. Thanks very much for the opportunity to present, and maybe if there are any questions, I will do my best to answer them.
Thank you so much, Foshilar. Really interesting presentation. I just included your website link on the chat so all the participants can directly link. And again, this video will be shared hopefully this week and together with the PowerPoint presentation so you can look at the Cordis link and the social media links as well. Thank you so much for your time. And maybe at the end, we'll have more questions on the Q&A sessions. We can next follow with the Intelligent Project, Niels Peter Wagner from SINTEF. Thank you so much for joining us.
Yes, good morning, everybody. Do you see my screen already?
Not right now. Only your face.
Okay, let's try now.
Yeah. Just a second.
Now we're here. Very good.
Yeah, all good.
Yeah. So good morning, everybody, and thanks for having me. I say hi from Trondheim, Norway, and I'm the coordinator of a sister project to HIGHSPIN that actually includes very similar chemistry than what Boschina just presented to you. But I will give some different use cases. So our project Intelligent stands for Innovative and Sustainable High Voltage Lithium Ion Cells for Next Generation Batteries. Yes. So we also answer the call by the high voltage route, combining LNMO cathode together with a silicon graphite anode. Intelligent has a duration of 42 months, and it is about to finish in May this year. So I guess we are further ahead. Our total EU budget, or total budget, is also the same of 8 million euros, where we have 6.8 from the Commission, and then we have two partners, respective from Switzerland and the UK, that come with their own money in this case. SINTEF, located in Norway, we coordinate the project. We have industrial partners in Denmark and Germany and in Spain. We have research partners as well in Germany, Switzerland, Austria, Spain, and the UK next to us. So we are a bunch of research institutes, industry partners, and the University of Oxford as a pure academic partner. And we develop safe, sustainable, and long-lasting lithium-ion batteries combining high-voltage cathodes and high-capacity silicon anodes. So the targets that we set ourselves is to make these cells as 20 ampere-hour automotive pouch cells that operate at 4.5 milliamp hours per square centimeter aerial loading. And by this, we could achieve energy density values of up to 950 watt-hours per liter or 350 watt-hours per kg at cell level, with a price tag of below 100 euros per kilowatt-hour at pack level. Also, we answer the call by power capability of up to 1500 watts per liter or 700 watts per kg. And the cell is supposed to be cyclable for 2000 deep cycles down to 80% residual capacity. To achieve this, we set ourselves some technical objectives, where the first one is to achieve energy density and fast charging targets by balancing the need to include a high amount of active material in the electrode structure to achieve the energy density, but also facilitating transport of mass, charge, and heat for high power operation. This is TO1. Then we have TO2 as the refined approaches to stabilize interfaces for long cycle life. So we work a lot on electrolytes to stabilize the SEI on the anode side, but also on the cathode side. The third technical objective is a scale-up of sustainable and low-cost manufacturing processes. So our cells are also based on aqueous processing of the electrodes, and furthermore, also our silicon graphite composite electrode is produced by hydropower in Norway, so by clean energy. And the third one is to encourage the industrial acceptance of our solution. And in conjunction, of course, we have two non-technical objectives, where the first one is to ensure compliance with the EU battery regulatory framework, as well as to maximize our impact. So if we talk about our project in a nutshell, and we can envision a battery where we work on the processability and functionalization of inactive material in the battery, which has been done in our labs as well as our partners' lab in Barcelona by IREC. We work together with an industrial partner from Norway on anodes, whilst IREC worked together with an industrial partner from Denmark on cathodes, so that's Topsoe and Vianode. Electrolyte development has been done in conjunction between EMPA Labs in Switzerland and E-Light in Germany. And upscale or cell making has been done at labs of AIT, together with custom cells that was planned, that was later on taken over by us. And then we have work on modules and pack level by Mio Battery from Spain, together with IREC, and all overarching multi-scale modeling activities by our University of Oxford, David Howie, and us here at SINTEF. Again, very much alike in HIGHSPIN, we have developed our chemistry in two iterations or generations of versions. We now just have a look at the second or final iteration, as the first one is some years old already. So our final cell chemistry comprises optimized silicon graphite anode delivering at least 850 milliamp hours per gram, together with a capacity optimized advanced LNMO, which is also aqueously processable, which was designed at Topsoe Labs. Then we include binders, functionalized binders, as well as separators that include self-mitigation and self-healing functionalities. and also a final optimized high voltage electrolyte spun out by eLight and Amper. And of course, our electrode structures are also kind of optimized by modeling inputs from Sinter von Oxford, and then the final upscale. I will come back to that. So I would also like to give you some small highlights or examples. The first concept I would like to introduce you to is called self-mitigation. So cycle life enhancement by self-mitigations. We're probably all very well aware, working in the realm of silicon, by the term self-healing. This concept is a little bit different. So here we look at an LNMO cathode, and we are all quite aware of the challenges working with high voltage materials and also working with cathode materials in general that contain manganese. As chemists, we all love and hate manganese. It's a very nice and green element. The problem is that the 2+, the divalent state, is highly soluble in electrolyte. So in LNMO's case, both manganese and nickel can leach out from the cathode. They will reach the anode, and in short words, they will poison the SEI. So they will electroplate on the SEI and cause more side reactions in the cell. So our concept involves the binder and functionalizes the binder in a way that it can interact with any divalent species dissolved into the electrolyte and trap them, and then instead releasing further lithium ions into the system, and hence kind of interrupts this evil cycle. At SINTEF, we've been working quite some years with polyacrylates as binders for cathodes. And here's an example of our research prior to Intelligent. We worked on lithium and sodium PAAs. And by partially neutralizing them, we can actually get really nice processable binders that have performances as good or better than PVDF. We continued this work in Intelligent, and we can happily say that our binders actually outperform PVDF references, and in our opinion, they work better than CMC binders. Here's an example from single layer pouch cells of our LNMO material with our binders compared to PVDF baseline. Also, everything in LNMO graphite setup. And we get higher capacity and better retention, higher Coulombic efficiencies, and we could also measure high degrees of transition metal uptakes by the binder, and not only transition metal, but also HF scavenging effects. That really makes a difference in cycle life, especially if we look at the whole thing at 50 degrees, where we all know that LNMO has massive problems, that we can really outperform PVDF-based electrodes here. So that was the first example I wanted to share with you. And the second one that Boshida already also talked a little bit about is the long road to electrode upscale in all these projects. So we're very happy that we can say that we managed, even losing our cell manufacturer, we managed making our silicon graphite anodes, which in honest and quick words wasn't all that difficult, as silicon having such a high capacity. We don't need two thick electrodes here. But we also managed to make LNMO cathodes aqueously processed with capacities exceeding 4 milliampere hours per square centimeter. We worked quite a lot on the chemistry and on the processing, and we were able to achieve LNMO cathodes that have through plane resistances that are not far off the regular 2 milliampere hours per square centimeter in our final generation. And also the adhesive strength of our electrodes is much better than with a PVDF reference. This is an example measured at our colleagues from AIT. So here is an example what our electrodes look in cross section. So they're nice homogeneous. They were calendared to about 2.4 grams per cubic, and based on a single crystalline LNMO material. As my proud colleagues, when we made over 100 meters electrodes, and of course we didn't really want to waste these 100 meters, so we did a lot of tests initially on how to optimize the separators that we put into these cells, and also how to optimize the formation protocols to really get the best out of our electrodes. And that was a big success. So in the end, we at our facilities built over 60 multi-layer pouch cells we could not make 20 ampere hours with our equipment, but we managed to make 15 ampere hours pouch cells that our partner from Spain, Mio, in the end integrated into their models. So they adjusted the models for the new cell size. On the right side, you see and just example pictures of our cathodes, the jelly roll and the formation unit. And that also just brings me to the end already. I would, of course, like to thank all the project partners for their contributions, all my colleagues at SINTEF. And I also would like you to visit our webpage or our LinkedIn page and get into contact with us. With that said, thank you very much.
Thank you so much, Niels. I also shared the Intelligent website on the chat, and
Thanks a lot.
congratulations on all the work. It was very
Thank you.
successful. Yeah, thank you. So then we can follow with NEXTCELL project with our project coordinator, Sarah Daneshifar. Thank you for joining us. We have a couple of questions, but we will leave it at the end for the Q&A session. Welcome, Sarah.
Hello, can you hear me?
Yes, all good.
Okay, great. So I am on the share. I hope you have my share.
Yeah, we can see
Okay,
you.
great. So let's go. Hello, you can hear me from Paris. I'm presenting NEXTCELL project. As the other projects, we are also aiming toward the next generation of high-performance lithium-ion battery cells. And in NEXTCELL, we are 17 partners from different states of Europe. You can see the names from industrial, academic, and university. Also the institute. The coordination of the NEXTCELL is FEV. We have SIE as the financial coordination of the projects. Also Avesta as the technical coordinators. So the overview of the consortium, as you can see, the project as the other two other projects presented are from Cluster 5 2021. We started 2023 48 months projects, and 17 partners from different states, and the project budget is about 8 million euros. The overall goal of the project NEXTCELL is, as presented, first is to provide a new lithium-ion jellified cell generation by high capacity and high voltage applications. So in this project, the aim is to provide the full jellified cells, cathode, all the components. By saying jellified is cathode materials, anode materials, and separators, electrolyzer, electrolytes on the jellified form. So the aim is to have the high capacity, high density jellified cell through the NEXTCELL. So what are the objectives and what are the goals of the project? Mainly having the LMNO and active materials, having the high energy density in the produced cell, in the developed cells actually. To achieve that, one of the aim is to adapt mathematical models which help us also to adapt and to optimize the design and to concepts. Also using we are going to produce billions of these cells. So for this reason, we need to have the cells which are cheaper, safer, and of course sustainable. So these are the objectives and the goals of NEXTCELL cells. To to achieve this, so we fixed some outcomes on that. The first is to develop all the materials on the gelifying concepts. Then prototyping the gelified salts to TRL6. Saying so, we start from the coin cells to laboratory scale, and then to the cells in different capacities. We'll get to details later, and as said, so also to have the modeling of the gelified cell, which help us also to advance later on the next developments. And of course, to prove that, one of the main outcome of the project is to evaluate the technical safety, sustainability, and the cost improvement to these jellified concepts. How the project is structured and what are exactly the objectives and the aims on the project, as presented also in the two others projects. In this, in NEXTCELL also, we are trying to work on the active materials, on the anode and cathode, not only for the process and gellifying, but also about the materials using. So here, one of the main objective is to develop high performance silicon and LMNO based cathode and anode. Thereby saying so, for the silicon carbon materials, we are targeting to improve capacity and cycling stability, which are a critical challenge for silicon-based systems. One of the important aspect of this project actually is the transition from conventional NMC cathode to LMNO, as also mentioned in other projects, and which is focused on eliminating cobalt from the system. So in the other project, they try to get into the challenge dealing with LMNO. I will give you some words on the advantage using LMNO, why we aim to go through LMNO is like the advantage that its LMNO chemistry brings to the table. It operates at high voltage, around 4.7 volts compared to NMC, and that's give us this availability to go for high energy density at cell level, which is the key requirement for next generation of batteries. Then not using cobalt materials help us to address some critical issue, means like cost reduction, which is one of the other goals of the project. So because as you know, cobalt is one of the most expensive component in NMC. Then supplying chain security, which is like helping us by reducing the dependence on the geographically concentrated resources like cobalt. And then of course sustainability, that could be that is one of the today's concern in the battery industry. So this makes LMNO a much more scalable and future-proof solution for this generation, and that's why we are all talking about LMNO cathode-based like materials. However, it has its own challenge, and it is mentioned in the other projects and also in NEXTCELL. Apart from these challenges with LMNO, we are dealing another challenge, which is gellifying also. So it's add another like challenge to the project, but it is not to stop it advantage, and we are trying to prove that this is possible, and we had some promising results which confirm this choice of going through these materials. Another aspect of NEXTCELL and objectives, which is also very important, is the process development. So then we are trying to go through the jellified electrodes and separators, but what is proposing here is what is innovative. What is another innovation of the NEXTCELL, we can say, is the solventless process for fabricating jellified electrodes and separators. So as you know, the traditional electrodes manufacturing relies on solvent-based slurry processing, but here we are using solventless, and we are trying to address the manufacturing of jellified cell by solventless process, where we where the active material are mixed with a polymer matrix and go through the paste to the jellified forms. So that also this innovation also help us to get to the key advantage of like reducing the energy consumption, which is through the solvent based process is one of the main disadvantage, high energy consumption. Then help us to have more environmental friendly manufacturing process. Then yeah, here we are also using we are also proposing to go through the coin cell, like the development is through the coin cell to the single layer pouch layers and to the different like scales. So what we propose in NEXTCELL first is in the coin cell, then 500 milliampere hour, and then going through 5 ampere hour of cylindrical cells, also 20 ampere hour of pouch cells, which will be which are going to be electrochemically tested. So the electrochemical characterization will be checked on the cylindrical cells, also on the pouch cells, for validation of the parameters, and then aging protocols and safety tested will be also done for the both for the 3 different cells produced in the NEXTCELL. Also regarding the sustainability and the cost analysis, also we have the objectives of the process, which is developed. So to I think I need to accelerate on the project structure. So the project is structured in different work packages in the as explained. The main aim is to have the prototyping from the material and cell components development to large scale jellified, as explained. So we will have in the first step in work package 3 and 4, we will in work package 3 we will have the material and we had actually, because it is finished, material and cell component development, which is like delivered now. We have the cell. We have already developed this phase. In the small scale jellification cells, we are in the process, and we go up to 500 milliampere hour development of jellified cells, and then we will scale up to large scales to 5 ampere hour cylindrical and 20 ampere hour of pouch cell. As said, so we have modeling and simulation partners who are active on the on that side to help during the project on the optimization of the concepts, also the safety and cost analysis that we have. To go through the achievements, I quickly mentioned that we successfully achieved like the main objective by developing optimization advanced solventless process for lithium-ion battery at laboratory scale. We identified optimal materials and formulation for electrodes and electrolytes, demonstrating promising electrochemical performance and processability. While the technical challenge remains particularly in achieving the ideal balance on the properties in the gel separators. So we are dealing for the moment on that. We had the baseline definition and qualification LCA and cost performance. So cathode and anode have a higher environmental impact compared to electrolytes, and raw material account for approximately 56% of the cell costs. The preliminary LCA analysis of material used in the battery cells and recycling process flow sheet are defined by the partners. Here you can see about the model which is developed and on their validation, because in the previous model we had less model dealing with LMNO also in the jellified cells. So here we developed this model and we are going through the validation and to finalizing the model. Also our colleagues from FEV use also for the their their the inputs from the established like cost modeling approach to determine the impact of jellified cells to jellified cells materials actually, and the production steps to the cell costs. So here we start from the inputs from partners on including material costs, cell design, parameters, and production scenarios like volume, energy, and labors. Then these inputs fit into the cost modeling, which is bottom of cost model. On the material sides, we define a virtual cell design to estimate weights and dimensions, and on the manufacturing sides, we simulate the full process and associate like the cost. And finally, we obtain a breakdown separator contributing from chemistry, design, and considering manufacturing and margins. I think I finish in time.
Yeah,
Trying
you're in
to keep
time, Vera.
2 minutes.
You're in time.
Yeah, thank you for inviting us also in the cluster. It was a pleasure, and we are here to answer your questions if you have any. If you need any more information, please drop an email or contact us directly. Thank you.
Thank you, Sarah, for the presentation. I also shared the website link.
Thank you.
There's one question for NEXTCELL, but we will wait for the end of the presentations.
Okay,
Thank
great.
you. So, I will present Hughini from the SiGNE project. This is the final of the cluster, and then we'll move on with BATMAX. Welcome, Hugh.
Thank you very much. Can you see that okay?
Yeah, all good.
Fantastic. Okay, so it's great to see so many kind of common issues and items flagged from the various projects, the sister projects. So I'll just briefly introduce the consortium from the SiGNE project. So it's a 15 partner project. So the budget was 8 million for the overall project. We're representing 8 European countries. I think we're on a similar timeline to the HIGHSPIN project in terms of it being a 48-month project. So obviously it is it's coordinated here in the University of Limerick. So I'll briefly kind of flag the different areas of expertise for the various partners. So we're focused mostly on the anode material here in the University of Limerick. In analog devices, they're looking at the battery management system. SK Tests, they're looking at the kind of recycling side of things. Solvionic obviously are focused on the electrolyte upscaling. We have Siditech who are looking at the kind of full cell optimization and electrode processing. We have the University of Jena who are looking at the electrolyte formulation. We have ZSW who are looking at the cylindrical cell fabrication. KIT are interested in the cathode material development. DLR on the modeling side. Delfort are looking at the separator development. So we have a nice separator concept using paper-derived separators. Sapienza are looking at the cathode material modeling, and they're also doing some nice gas evolution analysis within the project. We have CRF and Ferrari, who are the end user EV partners on the project. So they're providing really good insight on the needs of batteries for automotive applications. We have Temec, who are looking at the upscaling of the anode material. So they're developing custom reactors for the development of our anode materials. And finally, Sidrabe, who are looking at the pre-lithiation of the anodes for us. In terms of kind of our overarching objectives, these are obviously very high level. What I'm going to try and do within the 10 minutes or so that I have now is to just give some highlights in terms of the different components and some of the developments that we've had so far. So obviously we're developing a new lithium-ion chemistry. There's lots of overlap from what we've heard already in terms of we're looking at the various components within the cell. We're trying to use modeling guided approaches, very much focusing on the mechanistic side of things where we can use our materials analysis to try and improve the materials that we have. A prototype validation that also includes our BMS from Analog Devices, and then all of the kind of performance targets that have been flagged before. So making sure that they're cost effective, that the production and the IP is kind of European based, and also within that focus around sustainability, circular economy, and recycling. So we've kind of addressed all of those various components within the project. In terms of our overall cell architecture or cell design, you see at the anode side, we have a silicon nanowire graphite anode material that you'll see here. We're looking at a range of different electrolyte components, but glyoxal-based is kind of the driver on this. It's a paper-based separator that we have, and then it's a nickel-rich single crystal NMC where it's cobalt poor. So we're talking about 4% cobalt is the kind of indicative range of cobalt within that. These are our targets then. If I bring in the specifics of the different components, you'll see, like the previous speakers, we have a number of generations of materials here. And what we did basically was primarily focusing on the increase in the silicon content. So you see by the end of the project, we're at 30% silicon content here. What that allows us to do in terms of our total anode capacity is get up to around 1,000 milliamp hours per gram. And that allows us then to target energy densities that are greater than 430 watt hours per kilogram at the cell level. Okay, so very quick highlights on some of the anode components. So as I said, these are silicon nanowire-based materials. So one of the main issues that I'm sure people are all aware of is upscaling these materials. So we have lots of expertise on the lab scale development of these. This is a nice stylized design of the reactor that we have. We've now been able to progress where we can produce 1 kilogram of these active materials and show the path to making these feasible beyond our kind of previous capabilities. You'll see a number of different images down here. The details aren't so important, but what I'm just showing are different snapshots of the materials from different zones within this newly established reactor. So what we had a lot of upscaling issues around compositional homogeneity. So we wanted to ensure that we had the same silicon content across the various zones within a reactor, and we've been able to achieve that now. So we can reproducibly make silicon graphite composite materials with up to 30% silicon content. And what you're seeing here, just as kind of high level electrochemical performance, is our generation 3 material has 30% silicon and our generation 2 is around 25%. So essentially we can tune the silicon content within our anodes, and we've now been able to deliver anode materials that have capacities over 1,000 milliamp hours per gram. On the electrolyte side of things, so again, as I mentioned, it's around these kind of glyoxal-based electrolytes. So we have had lots of issues that we needed to address here in terms of the cathode compatibility, but also the anode compatibility. We had some side reaction issues with cell components, for example. So what we've been able to do through the partners who are University of Jena and Solvionic is identify ideal electrolyte components and compositions that are compatible with our cathode materials, and also with our anodes. Okay, so there was lots of nice electrolyte design that went into this, finding the correct electrolyte additives that would allow us to deliver this type of stable cathode performance that you see here, for example. On the separator side of things, so these are cellulose-derived fiber separators being developed by Delford, and they have developed really high-performance non-polymer-based separators. Again, what we found is they're actually beneficial for the anode side of things. When you move to higher silicon content, obviously you'll have material expansion and contraction during cycling, and these paper-based separators seem to be able to buffer some of that volume expansion that we see there. In terms of the electrolyte compatibility as well, these have really good electrolyte uptake values from what we have seen too. On the cathode side, it's been led by KIT. These are our single crystal NMC materials that you see down here. Again, with cobalt poor, so it's around 4% of cobalt content. And what they're really focused on, again, because these are aqueous processed, is they want to do surface coatings to allow for increased stability of those. What you see here is these are just kind of indicative values. So you have a pristine material here in gray, and they looked at different degrees of coating on those active materials. And what they found in a lot of cases is that there's almost a sweet spot in terms of the coating amount that you have. So in this case, it was this pink component here where they were able to find the right balance between coating thickness and cycling stability. So overall, the materials, these are a little bit old in terms of the data that I'm showing. There's some more that's been developed for publications, for example. There's much longer cycling stability now for these active materials. So these single crystal cobalt poor cathode materials seem to have really good long-term cycling stability. And again, the voltage fade that is associated very often with these high voltage cathode materials doesn't seem to be as pronounced as the previous generations. On the modeling side, again, I'm trying to keep this as high level as possible, but give you an idea of all of the various activities that are going on. We want to ensure that modeling is kind of integrated at the material design level. So it's been used as a tool to optimize our active materials and also to kind of explain some capacity fade mechanisms that we have. So as I mentioned, this has been done by DLR primarily at the anode side and Sapienza at the cathode side. So they're combining kind of multi-physics models, things like COMSOL, for example, to understand the different processes that are going on during cell cycling. So they have a nice kind of pseudo 4D model that has been developed at DLR, which can allow us to understand some of the processes that are going on in our cells. On the material upscaling, so this has been a really important part of the project. Obviously, we want to develop processes for the anode cathode electrolyte separator to make sure that they're all readily upscalable beyond the end of the project, and also to make sure that we can show these within our prototype level scales. So again, this is our idealized depiction of the anode material upscaling. So as I mentioned, we have been coming from being able to produce grams of material, and now we can produce at the kilogram scale of our silicon nanowire graphite composite. And then on the cathode side, this is being done by ZSW, where they're looking at the production of these single crystal NMC, where it's very cobalt poor. So we have these nice upscaling approaches for each of the various components. Particularly Solvionic, they can go well beyond the scaling needs of the project. You know, rather than liters, they can talk about hundreds of liters. And at the separator, it's a readily upscalable process from Delford. And then the final component, again, is kind of a catch-all. You see there's lots of activities within the project. Is looking at the full cell testing, recycling, BMS, and the prototype development. Obviously, we want to take a lot of the heavy lifting here has been done by Sidotech, who have done what we call the full cell harmonization testing. So they do kind of going from coin cells up to single layer pouch cells to test a lot of these different combinations and permutations of materials as we go through. So they have really delivered lots of nice data along the way, allowing us to benchmark these different generations of materials and kind of iron out some of the compatibility issues before we move up to the larger scale. So they are also coating the electrodes for our cylindrical cells, which will be used in the demonstrator at the end. Within SK Test, they're doing the recycling of these materials. So even taking the old coin cells that we would have made in the lab and trying to extract out the materials from them. Finally, then, is kind of a timeline of this. This was obviously used in the initial proposal. This is where we were at in terms of the initial chemistry identification. Basically, what we've done is taken all of these various components and taken them from TRL4 up to where we want to be at the end, which is at a TRL6 demonstration. So as we move towards the final aspects of the project, we've a couple of kind of outstanding things that need to be delivered, which is obviously the final cylindrical cell and prototype testing. So that's well underway. It's just to actually run the testing at this stage, which obviously takes time. The recycling demonstration of the materials. And now that we've identified our optimized components, is looking at the LCA and LCC of the materials. We have had a number of publications throughout the project, but we're now at the period where we really want to maximize our output and dissemination of the results as well. So hopefully that was a very brief. I know there was lots of information there, just to give you a flavor of some of the different scientific components that are within the SiGNE project. Thanks to everyone for their attention, and I'll hopefully be able to answer any questions that people may have.
Dear Hugh, thank you so much for your presentation. There's actually a couple of questions that we'll leave to the end. And before moving on with the BATMAX project, I wanted to remind everyone of the participants that they can submit the questions in the chat. If you're on the phone, the Q&A button is not available, but you can do it on the chat. And speaking about dissemination of the cluster, actually we have a joint video that it's on YouTube. I will share the link because we'll have no more time. But actually we applied to the booster service, and together with the 4 projects, we developed this audiovisual service, and it's a video of this overview of the projects. So thank you, Hugh, again for your presentation. And then we have Prasant Singh from BATMAX project that he will explain the overview. Welcome, Prasant.
Hi, just
Hi.
a minute.
No worries. We see the,
It's my screen visual.
Yeah, we see
Okay,
perfectly.
perfect.
Thank you.
Okay, first of all, thank you, Rocio, for inviting this webinar. And I will like to present this BATMAX and mostly focus on one of the tasks. So let's move on. So BATMAX projects is having the 14 partners from the 9 different countries, and the project will complete this summer, but we are expecting some maybe we are expecting some more times to complete the deliverables. So here I would like to present the basics about the objectives of the BATMAX and approaches, how we approach to fulfill that objectives. And then I will mostly focus on one of the major tasks of this BATMAX, how this digital twin is a major task for this BATMAX, how it is integrating from physical layer to the cloud layer. So main objective of this BATMAX is to create a next generation of the battery management system based on the large amount of the data. Data could be experimental, operational, or synthetic data, and also to create adaptable physics-based models or suitable reduced order models for the both physical BMS algorithms and real-time multi-scale digital twins. So maybe I can take the ledgers. Okay, so for this BATMAX, set the path for the advanced next generation data-based adaptable battery management systems capable of fulfilling the requirements of the various mobile and stationary defined use cases and applications. And for this role, battery system, as we know that is the key enabling technology between this green shift in the transport, energy and mobility applications. And it is evident that multiple combinations of the requirements and use cases and profiles are placed on the battery systems to need to understand what are the requirements from these different use cases. And in BATMAX, we choose 4 different profiles. One is the maritime profiles, then these non-road mobile machines profile, and then heavy duty vehicles and stationary applications. And these profiles which are should have the coming the different things like the temperatures, average SOC, depth of discharge and fast charge and discharge requirements from the different uh, use cases. So here, this slide showing the overall conceptual flow of these whole BATMAX projects. So here we are taking the different kind of the parameterized data. Data could be the lab data or the experimental data or hill data, and then we'll create a digital twin of the battery, maybe equivalent circuit based models or physics based models or machine learning AI data driven based models. And here it is showing the different chosen profiles and how the data is flowing in the real time to the cloud to improve the safety, reliability, and cost of the battery, just to understand with these profiles how it behaves. Now, this is the here I will more bit specific on this one of the task, that is the digital twins. So how we set up this task uh, in this project. So this is the overall pictures of the architectures from this physical layer to the cloud layer via edge device layers. So here at the physical layer, it consists of a development PC where we developed a plant-based battery models. I will explain more in the next slide how we developed this battery plant model. And then we have a target real-time performance machine to uh, provide the interface, and then to emulate the battery electrical and thermal behaviors. We have these battery cell emulators and fault insertion unit and temperature sensor emulators. And then we have this Fox BMS master controllers that comes from the Fraunhofer side uh, to check the BMS functionalities, like it may be balancing, SOC estimations, or protection. And with this, we have a Fox BMS slave that also can we say that cell monitoring unit that is connected to these emulators. And then we have a Azure-based IoT edge device that is acting as a mediator between this physical layer and the cloud layer and sending data to the cloud side. Okay, so here we set up this to a hill-based environment in VTT. And here, why we did, I will go a little bit in the background about this battery and importance of these embedded controllers. As we know that battery are the importance in the decarbonization of this transport and electric power supply. And also embedded controllers needs to be managed and controlled with this kind of managing this battery management systems. And every battery has their own controllers known as battery management systems, and testing of those BMS should be safe and reliable according to the today requirements, but it is very difficult, kind of cumbersome or bulky to testing this BMS with real genuine battery. But and also testing those BMS algorithms with the genuine battery uh, is difficult, because battery we have differently over times and also have their different charge discharge cycles, and it is also very difficult to produce that core BMS algorithm such as cell balancing and then SOC estimations, like to complete the one charge discharge cycles may take several hours to the bigs. So it is longer time taking process, and also testing those BMS at high voltage, high current, high temperature is not safe. So, but this all issues can be solved by setting a battery digital twin known as hardware in loop setup. So here it is showing this whole setup, and for this firstly, it is showing the model in loop desktop simulations. So here, firstly, we make a 48 volt NMC battery system plant models, and to that are series connected in series. Cells are connected in series, and each model is modeled by the second order equivalent circuit. And these parameters that are used in these models are derived in our lab, and these parameters have the typical operating conditions like open circuit voltage and SOC characteristics, then dynamic voltage and currents, behavior during pulsed load and transients events, and also it is temperature dependence behavior. So after this, the here this second order model and the Fox BMS functionality is firstly developed on the development PC and run in the model in loop simulation, and then we move towards the real-time simulation. So this developed BMS functionality code is embedded in the C code and then deployed on this speed code performance machine to execute check these any errors or how our algorithms is working. And after this, we went to the complete hardware in loop simulations. So here the Fox BMS master is connected with his speed goat machines through the ethercat communications, and these slaves are connected backside of this emulator to measure the cell voltage temperatures. Now here this slides it's more about these components. So how these BC actually replicate the electrical behaviors and dynamics of the cell balancings, which are essential for the electric vehicles or any chosen applications that we should focus in these BATMAX projects. And we currently we are using this one emulators, and it is having 12 cells, and each cell can handle up to 5 volt and 5 amperes current through the for the testing. And also we have this temperature and fall sensor emulation for the thermal behavior or thermal stress of the system, and also to check the any kind of fault that may be faults, short circuits or over voltage, over currents or broken wires, so these kind of things. And then to check the BMS functionalities, these Fox BMS masters and controllers. Now, after this hardware interference during in the whole hardware in loop working flow, the second most important thing is to set up this EtherCAT communication and set up these blocks that coming from the library, because we are emulating the physical signals, signals, and we need to convert that physical signals to the isolated electrical signals. So here we did, with the help of this BMTS, firstly we set up the blocks, and to convert this physical signal to the electrical isolated signal, we need to write the write blocks to write that signals, and then we need to read that blocks. And this is also very important, when doing this writing and reading of this physical signal to isolated signals, the data is being converted. So it is very important to keep in the minds when we are reading voltage, currents, are enabling the each channels, what kind of data types we need to use. So it is telling more about that during all these battery cell emulators or temperature and fault sensor emulators. Now, after doing first step, making plant model, and then doing this hardware interference, the next important thing is to set up the communication between the Fox BMS master, I mean the device that is under test, with these emulators and the real-time target machine. So we need to set up these communications that we did through this EtherCAT, and can set up modules. It can be it is done. So after this third step, now when the can setup and every step is done, we need to send the pack the message and unpack the message, or also we can I can say that during that after transmitting, we need to receive that message. So here it can be done with the help of choosing these blocks. We did by choosing these blocks. So it can be done by two ways. One, if we have this DBC file, so we can do it easily by choosing this DBC file. Otherwise, we can do it manually by specified the signals. But the most important things by doing this packing and unpacking of the message is we need to put the CAN identifier number. That is very important during this transmitting and receiving of the messages. So here I will tell about these obtained results during these experimental setups. So first one is the graphical user interface that we made to monitor the BMS data and BMS. So here we model a 12 cells that are connected in series. So each cell showing the voltage, temperature, and SOC and imbalance current that is flowing with each cell. So this is changing according to this CCCV profile. So in this test, we use a CCCV profiles that was supported by Corvus, which was a maritime profile. So currently here it is constant current at very high rapid charge, and then constant voltage. So for the uh, safing of the cells. So after this, we also went through the check the how is the Fox BMS balancing strategy is working or not. So we triggered that cell balancing, and once we triggered, we found that the cell every cell voltage and SOC was increasing rapidly, and the imbalance current was flowing around 2 millivolt, but in this case it is set up around 80 millivolts. So to initiate the balancing, we choose cell 4. Any cell we can choose, but for examples we choose cell 4, and then find out the imbalancing itself for went to the balancing mode, and the imbalancing current here it is not showing because this graphics was not updated, was flowing around 100 milliamperes during the dischargings. And now this was about the graphical user interface for the real-time monitoring of the BMS data. And now here this figure shows the laboratory and hill voltage responses. together with the applied. Yes.
Maybe we can start closing so we can move on with the Q&A.
A bit faster.
Yeah, a little bit.
Okay, I think it is the last slide, so I will not take more than 1 or 2 minutes. Okay, so here it is showing the validation of our lab data and hill data. So it is also, and then the most important thing was to monitoring this temperature. So this is the cell temperature. That is the this is the set ambience temperature, and the cell temperature that was varying very close to during these operations, and this indicates that the limited thermal stress during this applied maritime profile conditions, and also stable thermal behavior during the test durations. So after this, we went to the cloud side. So here, after hill setup, the hill measure data, we went to the cloud side and through the Azure clouds. And on the cloud side, we received these messages and unpack. And here it is showing on the cloud, we were able to send in real time every cell voltage and temperatures. Yeah, so here, if I conclude, we firstly make the 48-volt plant model and then set up the hill environments, and successfully able to send these real-time data with different maritime profiles or different use case scenario on the clouds. Yeah, thank you.
Thank you. Thank you for your presentation.
Okay, I would like to take any questions.
Yes, we have 10 minutes for the Q&A, and there were a couple of questions on the chat, so I think it's better if I share my screen because I put them here. So this question, I think it was for every one of the project, like what specific data or tools could be shared across projects to accelerate progress. I don't know who wants to answer this.
I can start.
Thank
We
you,
will,
Bill.
of course, share all data that we can and are allowed to share. But we are right now in a process where we really accumulate all the data to share it with everybody interested, and we will do so using Zenodo. Because of course my colleagues developing this modeling platform BATMO that we are very happy if more people would use. So that's from our side.
And BATMO is called.
BATMO, yes.
And we can
you can find it online.
Online.
Give me one. I should know the link.
Okay. Maybe you can also share the link.
Battery is BATMO with 2t.org.
Okay, that's great. Yeah, and I think all of the projects have this Zenodo page with the public results. Thank you.
Yeah, also for NEXTCELL, we have several data published on different conference, and so that are the things is shared already. But about the rest, that's we are very still to the end of the project, and of course there are some applications which is in simulation. In which extent we can share that to the public, that would be besides the end of projects.
Perfect. And we understand that a couple of projects are ending very, very soon.
Yeah.
But these public results are, of course, available in Zenodo.
Yeah, that will take more time.
Yeah. So, Sarah, we have this question for you, if we want.
Yeah. What are the main? I'm reading the question for the audience. So, what are the main challenges in scaling GEL into industrial production? By that, they mean with existing lithium manufacturing lines. Good question. Shows the vision toward commercialization. In NEXTCELL, we are aiming to go for TRL6 to commercialize to prototype the upper scaling of the cells, but this question goes to the production and using the existing lithium-ion lines. as in the NEXTCELL, we are using the cells of NEXTCELL has two characterization, jellification and solventless process. So in some extent, we can use the existing lithium-ion line, but some steps really need significant modification. So, for example, for existing like lithium-ion lines, they are optimized for liquid electrolyte, while we are using like specific jellification systems. So that needs modification. We are using solventless process, which needs like uniform mixing and coating, also like about controlling the electrode thickness and dry process that we are scaling. So different steps need to be adapted. However, in some extent, some of the existing line can be used mainly on the mainly on the assembly or the other aspects, but main challenge goes through the jelly to gel electrolytes.
Thank you, Sarah, for your answer. And the final question, if there's not a new one on the chat for Intelligent, how did these new electrolytes improve safety in terms of flammability and thermal stability?
Yeah, I'm not quite sure if this question was actually to us. I mean, we also developed new electrolytes, but I haven't really talked much about electrolytes. In I can just answer for our project. In our project, we work on liquid electrolytes, and they are, I would say, as flammable or non-flammable as state-of-the-art electrolytes are. And in general, I guess in most of our projects, when we're working with the high voltage spinel, we will have a better safety profile, I guess, than the SiGNE project working on nickel-rich layered oxides. But I guess we all still have charcoal in the anode and an organic liquid, most of us. So these electrolytes will still be flammable, and our anode will still burn. But to varying degree, our cathode is quite safe, very safe. But I don't know if this question was really for me.
It was written on the chat.
Yeah.
Yeah. But thank you, Niels, for answering.
Thank you.
So if there's no other question, we're just in time. And I want to thank all of the speakers and all of the participants for joining this morning. I think today's discussion clearly shows that our collaboration is a key by working together, and we can accelerate innovation. Thank you so much. The recording will be available soon, and we will also share the contacts and all of the links. And thank you, Niels, for sharing the batmo.org. That's on the chat.
Thank you.
Thank you.
Thank
Thanks,
you.
everyone.
Have a great day.
Thanks, everyone. Have a good day.
Thank you.
Have a good day.
Bye.
Bye-bye.
Bye.